Algorithms are at the heart of computer science and therefore all software development. Today we'll explain what the term algorithm really means. You've probably heard it in the media, you've probably heard it in everyday speak, but do you really know what it means? Welcome to Kopec Explains Software, the podcast where we make computing intelligible.
Well, Dave, what is an algorithm?
Algorithm actually means something pretty simple. It's a way to solve a problem. So you have some kind of problem and you need a series of steps to solve it. Let me give you an example. Let's say you said, how do I get to the grocery store? And you weren't from around here. I could give you a series of steps to get there. I could say, well, go out of the house, turn left, at the stop sign, turn right. At the traffic light, turn right again. Then go 2 blocks, and the grocery store is on your left. That is an algorithm. Anytime you give somebody a series of steps to solve a problem, you're basically giving them an algorithm. Now, that's not a very interesting algorithm because it's so specific to that particular problem. What's more interesting are algorithms that can solve a whole class of problems. For example, what if I gave you an algorithm that was general enough that given a certain map, it could get you from any point on the map to any other point on the map? Now that would be a lot more interesting because we could use it to solve all kinds of similar problems. And if it could do that efficiently, then it would be really, really powerful. So an algorithm is just a way of solving a problem, and it's a way of solving it using a specific set of steps. And we tend to like algorithms that are generic enough that they can solve whole classes of problems.
So what makes an algorithm good?
There's really 2 things we look at as software developers when picking an algorithm. One is efficiency. And that can mean efficiency in terms of how much CPU time an algorithm uses, so how much does it tax the microprocessor. And memory consumption can also be related to efficiency. So does an algorithm use a ton of memory, or does it just use a little bit of memory? That's number 1. Number 2, as a software developer, we're also thinking about ease of implementation. So how hard is it going to be to actually implement this algorithm? What we really love are algorithms that are efficient and that also are pretty easy to implement. Those are the best algorithms. Now, there's often a trade-off in terms of efficiency in terms of time and efficiency in terms of space. They call it the time versus space trade-off. So oftentimes there'll be an algorithm that's really time efficient, but uses some extra space, or an alternative algorithm that is not as time efficient, but uses very little space. So all the time you're thinking about trade-offs in terms of algorithms, one versus another. There's usually more than one algorithm that can solve a particular problem. For example, sorting, let's say, a list of numbers. There are so many different sorting algorithms, and if you take a data structures and algorithms class, you're going to spend some time going through and learning 3, 4, maybe 5 different ways to sort a list of numbers. But some of them are more efficient for certain kinds of situations, and some of them are more efficient for other situations, and some of them are just really inefficient and you never want to use them. So there are multiple different algorithms often for the same problem, and we're thinking about efficiency and ease of implementation to really decide which one is a good one.
How do we measure efficiency?
Yeah, so I mentioned that the 2 kinds of efficiency that we're interested in are time and space means memory. So to measure time, we often can do something very simple, which is just start a timer. So you start your algorithm running, and the timer starts, your algorithm finishes, and your timer stops. And you processed a certain amount of data within that time. Sometimes there are algorithms that are really efficient when you have a small amount of data, and they're not so efficient when you have a huge amount of data. So you really need to keep in mind how the algorithm is growing. What's its growth rate in terms of its performance characteristics as the amount of data changes. So we can just use a timer for measuring time efficiency. For space efficiency, we often have other computer programs that measure the memory usage of our program. And the best kind of tools are actually called profilers. And we talked about that on a previous episode called Developer Tools, which I'll link to in the show notes. But a profiler goes and it can tell you both about time efficiency and memory efficiency of your program and kind of can take a snapshot of how the program is running and how much time and memory it's using at any given point in the program. And then you can look and actually play back its usage over time. And that can be just like an amazing and powerful tool. So we actually run experiments. This is where the science part of computer science comes in. People often wonder, computer science, it doesn't sound like a traditional science. And there's a lot of things that get thrown into the field of computer science, but there really is a scientific methods part to it. And this is where we use a hypothesis. We go and we want to test it. So we run an experiment and we run some tools to see how well the experiment actually ran. It might be something like a profiler running the same algorithm with different sizes of data, different types of data. And we see, oh, how much CPU time did it use when we had this kind of data and this amount of data? And how much CPU time did it use when we had this much different amount of data and this really different kind of data? And then we can actually see if our hypothesis was correct. How quickly did its performance scale? And then we can adjust our hypothesis or adjust our algorithm and do the experiments again. So that's the real scientific method, testing, finding our results, changing our hypothesis based on those results, and then testing again and doing this iterative process until we get to the best possible algorithm, or at least really have found out all the performance characteristics of some particular algorithm.
So, as a software developer, how do you choose which algorithm to use? Do you go through this scientific method each time?
As a software developer, you're often going to reach for the tools that are most easily accessible to you. And a lot of common algorithms are implemented in standard libraries of the programming language that you use, or in some very easily accessible libraries that everyone knows about. Let me give you some examples. So, for example, I mentioned earlier sorting, right? That's so common. That's something you always have to do. Almost never as a software developer would you go and write your own sorting algorithm. It would be very rare that you would have to do that today. Instead, your standard library of your programming language, whether that's Java or C++ or Python, is going to have methods built in for doing sorting. And you're just going to call those, and they're already going to be really optimized and really battle tested and proven that they work well. And you're not going to go write your own sorting algorithm. If there's something you need to do that's a little more esoteric, a little bit more outside of the mainstream, then you're going to go look for a third-party library to do it. And if there's no good third-party library, only at that point are you really in software development often going to go write a new algorithm from scratch. That said, you're actually always writing algorithms when you're writing software, because you might not be doing something as formalized as sorting, but all software is really just a series of steps to solve some kind of problem. It might use a lot of off-the-shelf, well-known algorithms to get there, but it's also going to have some of its own business logic, some of its own user interface logic. And all of that are little algorithms, little steps to solve little problems that your user is having as they're using your program that you're writing solutions for. You really are always doing algorithmic thinking when you're programming, but there's some people who do more deep algorithmic thinking, and those are people who we call computer scientists, who are really figuring out the most efficient way to solve some common or even not so common problems that other people run across.
How do we know that an algorithm is correct?
Most algorithms can be mathematically proven correct. Not all, but most algorithms can be proven using a set of steps in what's called a formal proof. Now, those of you that have taken college level math, and even maybe some high school level math, have seen proofs before. And it's the same thing. It's the same kind of proof theory that you would see in any other mathematical discipline that's used to prove an algorithm correct. And so we can be pretty sure that most algorithms that we run across are correct and that they're actually going to give us valid results. Now, there's another kind of math that I maybe should have mentioned earlier, and it's called Big O notation. And it is pretty specific to the world of algorithmic thinking. And it's about estimating what the bounds are of the performance of a particular algorithm as the data set grows. So how efficient is the algorithm as the data scales? And without getting into the specifics of it, it is a way that we can right off the bat, before we've even gone and run all the tests, done the whole scientific method, have some kind of idea of how well an algorithm performs. So we might know right off the bat, Well, this one, because of the upper limit of how it would perform with data sizes changing, it would probably be the better algorithm to choose than this other one that's going to really just fall on itself and not be able to handle large amounts of data. So just by using this big O notation and the tools behind it to actually come up with the notation, which are called algorithm analysis, we can actually be pretty sure how well a certain algorithm is going to scale as data sizes change. So oftentimes that'll be good enough for us for a first pass, but then we always want to run actual experiments with real world data because sometimes there's some constant time factors, things that the theory doesn't really account for that are going to impact how well the algorithm performs. Let me give you an example. Let's say we have an algorithm that is going to need to do a lot more network requests. Theoretically, when we look at it, it looks like it's going to actually perform better, let's say, with a large amount of data than another algorithm that doesn't make as many network requests. But the actual cost maybe of doing all of those network requests actually adds up, and then it actually ends up being the more expensive algorithm. And the theory didn't account for that because the theory didn't know just how expensive those network requests were going to be. So even though we have tools for algorithm analysis like Big O notation on its own is never enough. We also want to actually run experiments and see in the real world, given real hardware and real software, how well the algorithm performs.
In some of the talk about algorithms, I've heard a lot about bias in algorithms. Can you discuss that a little bit?
Absolutely. This is a very hot topic for the last 5 years or so, because there's been many important news stories that have broken about algorithms having bias. And we know that this does exist. And a lot of people wonder, well, why are people making these biased algorithms? There's a little bit of nuance to it. It's usually not the algorithm itself that's biased. It's often the data set that the algorithm is working on. Let me give you an example. Let's say I had an algorithm that was supposed to count how many cars come into my driveway. So I had a camera on my driveway and I wanted to know how many cars came in. So let's say that to train this algorithm, and let's say it was a machine learning algorithm, that's probably what it would be, right? There's other ways I could probably go about doing this, but let's say it was a machine learning algorithm. We'd have some big data set, hopefully, of pictures of cars so that we could learn to detect cars in an image. But let's say that data set of car images included red cars and blue cars, but it never had any yellow cars. Well, then even though the algorithm didn't know anything about the colors of cars, because it was trained on a data set that didn't include any yellow cars, it's not going to know that a yellow car is a car. So oftentimes it's not actually the algorithms that are biased, even though the media often uses the term algorithmic bias. It's often actually the data set that the algorithm uses where the bias actually comes from. Now, that said, it's absolutely possible to put explicit bias into an algorithm. So for example, we could have our car detecting algorithm go and have a particular point where it says, oh, this is a yellow car, just don't count it, right? And that would be very nefarious, but that's not usually what happens. Usually it's actually the data sets that the algorithm is working with that create the bias. And so we're seeing this in all kinds of places. Of course, there's been stories about facial recognition not working well with people of particular skin colors. And then there's also been articles about, and really exposés and news stories about bias in the Facebook algorithm and what it shows to different people and how it might sometimes actually reinforce our biases by showing us particular kinds of stories. So all this stuff is totally real and it totally is happening. But I think people should be aware that we shouldn't always blame the algorithm itself. It's oftentimes just a little more subtle than that. It's oftentimes the data set that the algorithm was created to work with, or that if it was a machine learning algorithm was trained on, that actually leads to the bias in the end result.
So it's really important as a developer who's working with a machine learning algorithm that they have as diverse a data set as possible to train it.
That's absolutely right. It's really important to have a good data set, a fair data set, a diverse data set that includes every kind of possibility that the particular algorithm could come across. All right, thanks for listening to us this week. Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
Thanks for listening to us, and we'll see you next week.
Bye.